Okay, so this is a presentation I gave to NOAA Fisheries in March as part of their 90-day review to see if steelhead should be listed on the Olympic Peninsula. This just covers the OESF. So we have 3 different monitoring programs going on right now. We've got our Stats and Trends program that Warren just talked about. We've got our validation monitoring program. This includes sampling 50 of the type 3 streams within the Stats and Trends program, a 13-kilometer section of the Clearwater River, and we just completed a 6-year study on the removal of a culvert in Bear Creek. We also have our T3 watershed experiment that does fish and habitat sampling. Here we sample about 16 watersheds, 2 sites per watershed. And we have 5 prescriptions that we're going to be looking at in the future, and that will probably be discussed more later on this today. The first question I wanted to answer was, where do we find steelhead? And what we found is they're pretty much in all of the gradients that we're sampling in our streams, so between 0 basically to 21%. And we find them about 26 to 34% of our monitoring type 3 watersheds, so the Stats and Trends watersheds. The next thing I wanted to present was a kind of a co-occurrence model that we looked at a few years ago. And this is just in the range of coho salmon, juvenile coho salmon. So gradients less than 9%. And what we found were that coho, sculpin, and cutthroat all had a positive relationship with each other. So if we find them in one stream, we're likely to find the other 2. With steelhead, we actually found a negative relationship with cutthroat, coho, and sculpin. And what we figured this meant, or when we looked into this a little bit, we figured that steelhead were actually in the larger watersheds that we sampled. And if you look at the range of our validation watersheds, if it stays here, or the steelhead watersheds, you see the steelhead watersheds are larger than our validation watersheds. Next, I wanted to look at the trends of juvenile steelhead. And to do this, I focused on 20 annual sites that we sample, obviously every year, within those Stats and Trends watersheds. So 11 of these streams we found steelhead in, juvenile steelhead in one of the years that we sampled. And what we see is that bottom green line is a very straight trend. So we're not really seeing increases or decreases of our age 1+ juvenile steelhead. We do see an increasing trend with what we call our age 0 trout, which could be either cutthroat or steelhead. And if we look at the trend of all of our annual sites, we do see an increasing trend from 2016 to 21. So when I first got here, one of the first things we wanted to do was understand what our current levels mean relative to the past conditions on the forest and stuff like that. So we did this analysis in 2019, and I'll show graphs like this throughout there, so I wanted to take some time and tell you what this means. So the dot represents the mean, the lines are 1 standard deviation. Our y-axis, we have our metric, in this case, fish per 100 meters. And then on the x-axis, we have our different categories. So we have production forestry, our reference forest, and ecological forestry is what we're calling our time period since the adoption of the Habitat Conservation Plan. When I have enough data, I also separate it into time periods. Oops. And what we see with our age 0 trout, we actually don't see a significant difference between our numbers now and the numbers we found in the 1970s, or somebody found in the 1970s. This isn't all that surprising because age 0 trout don't need as complex habitat. They can do fine in kind of shallower habitats and do fine. And you kind of see that in that trend line where we saw those increasing age 0 numbers, but not necessarily the age 1. Next thing we looked at were coho salmon. With coho salmon, we don't have as many streams available to compare. They're only in about 60% of our watersheds. But we do see a significant decrease in numbers and densities from our current, 2016 conditions to the 1970s things. With coho salmon, we really don't know what the cause of that decline is. They're anadromous fish, they go to the ocean, so there could be things going on there that are causing this decline rather than like local habitat, which I'm more concerned about. So next we go to age 1 and older cutthroat trout, which are really my perfect research specimen because they spend over a year within DNR habitat, and I can attribute a lot of their conditions to the local habitat. What we see with this is in 2016, we have a significant decrease between the 1970s numbers and similar numbers to the 1990s numbers. Now, unfortunately, we don't have enough streams with data to compare for juvenile steelhead. But when we look at that trend line in that earlier graph of age 1 and older steelhead, it is actually very similar to this age 1 and older cutthroat numbers. So we'd expect similar levels there. Now we're going to see what's going on in the upper Clearwater River. So we're going to go from our small type 3 streams to the larger river. One thing that really surprised me when I started doing the snorkel surveys on the Clearwater River were the amount of, or the lack of really large fish in the system. And you can see both these graphs, the 2 bar graphs are actually number of fish and not a density count because we have so low numbers. Juvenile trout, we actually have quite abundant numbers within the Clearwater, so those are a density graph. With adult steelhead, we've had a max of 7 adult steelhead counted in 2017 and a low of 0 in 2021. I do want to note in 2018 and 2020, we didn't complete a full survey due to rain and stuff like that, so I'm not going to really talk too much about those 2 years. I will note that we did move up our surveys to the last week of August from the first 2 weeks of September to kind of get better weather where we can consistently sample. Our larger rainbow cutthroat trout, we found anywhere from 60 to 130 over this 13-kilometer section. So what I consider very low densities. Juvenile trout, one thing I want you to remember with this, because I'll come back to it later, is that our reach 1, our uppermost reach, has consistently maintained our highest density of fish, and our reach 3 has maintained the lowest densities of fish. So now I want to kind of go from presenting some data to what I think is going on in the forest. And I think to understand our current conditions in the forest, we need to understand the past. And in the 60s and 70s, there weren't a lot of regulations going on, and even earlier in some cases, where they'd harvest through the stream, they'd remove wood from the streams, and this caused a lot of damage to our streams. We had a lot of landslides, a lot of sediment going in there, deepening in streams and stuff like that. Really, one of the last things we really thought about was just how much of an area we were harvesting and what was going on with that and the results of that. So to get an idea of what our forest looks like today, you can look at the age classes of the forest here in this bar graph of green here. You can see that most of our forests are between kind of this age of 20 to 80 years old. We don't have a lot of forests over 200 years old. Now the next question becomes is what were conditions prior to all this harvesting activity? And for this, I've always used this graph from Donato et al. 2020 that looked at what the forest would look like given the natural range of variability. What they found is that typically, on average, the forest, about 70% of your forest would be in old growth or mature conditions, most of that being in old growth. So it's a little bit different today. And the next question is, why does this matter? So to help answer this question, we developed this conceptual model looking at how different ages of forests relate to the in-stream wood. And what you see, and we've got 5 different stages from old growth. In old growth, we tend to gain wood just because of these large pieces of wood fall in the stream, and they're large enough that they sustain for hundreds of years and add to the wood in the stream. You go to stand initiation, it lasts about 0 to 15 years on average, and you have just the remnants from that last stand replacing disturbance in the stream that's starting to diminish. It goes into canopy closure stage, which is about 15 to 40 years, where you're not getting a lot of hardwood or recruitment, and what recruitment you're getting is mostly hardwood. Then you go to stem exclusion stage, which is 40 to 100 years. You're still getting a net loss. And even in the mature forest, you've got large trees, but they're still in the forest and not in the stream, helping things out. So I did want to kind of focus in on two different stages that we're kind of dealing with here. So we've got the old growth forest conditions. When you have these old growth forests, they're driven by these low severity disturbances. So you get these gaps in the forest, and you get light coming down, and you get wood going in the stream. And your forest is going to stay in this conditions for hundreds of years. And until there's some large disturbance here on the coast, it's likely a big wind throw event or something like that. They'll put all the wood down into the streams in the forest at one point, and then you go to stand initiation. The other one I really wanted to highlight was the stem exclusion stage. So this is where most of our forests are today. As you can see, we have very dense conifer-dominated streams. You're not getting a lot of light into the ground cover or into the stream. This kind of reduces productivity. And as you can see on the ground floor, there's not a lot of vegetation. When you do get wood recruitment, it's kind of through competition. So these larger trees are competing with these smaller trees, and the smaller trees are what's going in the stream. They're not going to be as impactful on the stream as the larger things. All right. So we're going to put all this together, and what you get under this succession is kind of what's called a U-shaped pattern of development. So you have your highest amounts of wood at the very beginning and the end of the forest stages. Now, to make matters worse, when the disturbance is forestry and you're harvesting through that riparian area, you're not getting that initial surge of wood. So basically, instead of starting at a high level and that's going to sustain you for about 200 years, you've got no wood and sometimes actually negative wood if they remove that wood from the stream. So this is going to delay your recovery of wood for hundreds of years potentially. So you may not see levels return to previous levels till 300-400 years old, depending on how much disturbance is in the system. Okay, so now we're going to switch from kind of my conceptual models to what we're seeing on the ground. And first thing we're going to talk about is stream temperature. And I'm going to go through a series of graphs, first kind of going to Warren's report, Stats and Trends report, and then go to that report that looked kind of our current conditions to the past conditions. And so this first one, we just talked about stream temperatures. Our stream temperatures have been fairly consistent. Obviously, there's variations by years, and we've had some weird weather things going on in a couple of years that have driven the changes. But from 2013 to 2020, if we compare those first and last years, the numbers are very similar. Now, if we compare our stream temperatures from our current data to the production forestry period, we do see a significant decrease in our temperatures. I do want to remind you these are the smaller streams. You would probably see more temperature effects in larger streams and things like that. We have very similar conditions to the reference conditions, maybe a little bit less. All right. The next thing I want to talk about was canopy cover. Like I said, we're in the stem exclusion stage, very dense canopy cover. We do see the canopy closure has increased from the first to the last measurement. Give you a few more seconds with that, but still very, very dense canopy cover. And how does this look between our three comparisons? So our production forestry, our reference, and ecology. We see significant differences between all three of these periods. So production would be kind of canopy right between the stand initiation and canopy closure. Your reference are likely more old growth or mature, and your ecological forestry stem exclusion. So we do see this really dense canopy compared to those two other periods. In-stream wood, we have seen from our first and last measurement, we saw decreases in in-stream wood density and wood diameter. And we do our comparison, we do see a significant decrease in our wood from the 1970s levels. As Warren mentioned, we did a more in-depth analysis of wood this last year. Here on my right, you see a bar frequency graph with kind of all the different diameters of wood we find within the stats and trends sites. And we've had about medium about 28 centimeters. And to compare this data, I've used this data from McHenry et al. 1998 that actually sampled some old growth sites within the boundaries of the OES a while ago. And what we found, the medium range between their 5 old growth sites ranged about 30 to 50 centimeters. They also had some second growth sites, and those were all had a median less than 30 centimeters. So our data fits very nicely within there. Okay. Okay, this is Warren's wood pool formation stuff. I'm not going to go over this because he covered it very nicely. But 16% of our current wood is creating pools. Montgomery and all found in their functioning streams that 20 to 60% of their streams would create pools. We also found a relationship between pool volume and wood volume. So as you get bigger piece of wood, you'll get bigger pools. It's a little bit of a noisy relationship, but we attribute this to the range of stream sizes and gradients we have. Now, I'm concerned about wood in our smaller streams. I'm really more concerned about wood in our larger streams. And this is back to that Clearwater River survey. You see we have very low levels of wood in all 3 reaches, about 6 to 10 times less than the levels recommended from Dominguez and Cedarholm in 2000, or the levels found by Peterson et al. In 1992. Now, this is context dependent. Reach 2 is a very bedrocky reach, so you wouldn't expect to see a lot of wood accumulate there. But reach 1 and 3 are both accumulation reaches where I'd expect to see more wood accumulation. If you remember back from our earlier graph, I said that reach 1 always has our highest density of juvenile salmonids, and reach 3 has our lowest densities. Oops. And so reach 3 has always been one reach I've kind of suggested for stream restoration in the future. One other thing I was asked to talk about when I gave this information was DNR fish passage barriers, and we've been very good at removing barriers in this district. And 450 barriers have been removed since 1999. There's only 8 barriers removing, and 4 of those are going to be removed this year there. Also wanted to get to a study that I just completed on the Bear Creek culvert removal, and this culvert would be considered about a 33% passable culvert using WFW's criteria. Okay. And what I assessed was 2 years pre-removal and 4 years post-removal, and we looked at both density and biomass. And what I found were no significant differences between before versus after or control versus impact. So when you have these partial barriers that we're removing, you may not see that significant upstream effect that some people are anticipating you'd have. So I guess my take-home message from that is when you're looking at culverts to remove, I'd look at the fish composition below and above the culvert and see if they're similar or not. If they're different, then you're probably gonna get a lot more impact from culvert removal than if you have similar species above and below. Okay, and with that, I think I'm done with my time.